patent which says that using HALT, one can estimate the mean time between failures. So here is the patent number, and basically the idea is that they are using this kind of an exponential acceleration model, so meaning that you have some kind of an initial reliability value or robustness value, then you do the HALT process where you increase the robustness and you get some kind of a quantitative estimate for that one, and then you can calculate the final failure rate estimation. So how this process is ongoing according to this patent. So it just have here the acronym. So CSS means cold step stress test, HSS hot step stress test, VIBE is the vibration stress test, RT is the rapid thermal cycling or shock, and CE is the combined environment, meaning that you combine the rapid thermal cycling and then the vibration steps. So basically these refer to the same parts of HALT testing as what we discussed last Thursday, previous lecture. So how is this then this let's say process ongoing? So first you start the whole thing by calculating the so-called initial mean time between failures or mean time to failure by BOM process. What is BOM process? BOM stands for bill of materials. So basically this just means that based on the components of the product, you calculate some first guess of the failure rate. So this could be now, for example, this mill handbook part count process or whatever way of calculating the starting point. So initial, you get some initial number for the failure rate or mean time between failures. And then you do the normal HALT procedures. So you do all these 5 different tests. And then what you do is you record the times to failure for each test. So pay attention now that now we are talking about times, not for example, temperatures or vibration levels, but times. So of course, this means that you need to be consistent with your time in every test. So for example, that you keep 10 minutes in every test, and then you increase the step and again and again. So now these values, what you have is the initial value, how much your product withstand these cold temperatures. So if you start from room temperature, then with 10 degree steps, you go downwards and you keep there every 10 minutes. So you have +10, 0, -10, -20, -30, -40. Then you find the first failure. It means that your time is 1, 2, 3, 4, 5. 5 times 10 minutes, which is 50 minutes. So then you have here 50 minutes. The same with the towards high temperature, the same with vibration, the same with the thermal cycles, and same with combined environment. So you do all these 5 tests through without yet doing any corrective actions. So this is slightly different than what was originally proposed, because there the idea was that in the step stress test, you always, when you encounter failure, you correct it and start again. But now you go through these 5 steps and do not do any corrective actions and just record the times to failure for each test. Okay, that's the first step. And now you have basically 5 numbers indicating the failure times in each 5 tests. Then you do the normal corrective actions. So you continue all these tests and you make the corrections, you change the components, you change the layout, you do some mechanical, improve the mechanical robustness by using some dampers or using some adhesives or whatever. So you do the corrective actions. And then what you do is you record the final numbers. So this T subscript improved means that what is the final number you kind of end up after the corrective actions. So now the point is that you have the initial values and then you have the final values, and now you, let's say, make a statistical estimation how much you have improved the relative life in each test. So basically this is now just an average of each 5 tests. So improved minus initial, and then you sum up all those 5 and divide it by 5. So basically this value here tells you on average how much reliability time is improved by these corrective actions. And then you use this R star as an indication of relative life improvement, and then you can basically get the improved value or the final value of your failure rate or MTBF by just multiplying the initial value with this relative improvement. So hopefully you understand my maybe confusing explanation. So starting point, you have certain times, then you make the corrective actions, you have final times, then every test you calculate the improvement, and you take an average of those improvements, and then you multiply the original value with the, let's say, relative improvement, and you get the final value. So now, of course, we already kind of had a critical look on what is this initial value, because it only includes the data coming from the components. So it does not include the system level effects and these kind of quality related things. It does not include, I mean, for example, manufacturing quality related issues. It can include the component quality related issues. It does not include the software issues, and there's several things which is kind of excluded from here. And then you multiply that, let's say, uncertain value with something which you calculate this way, and then you get a final number. So is this really valid or not? I think that depends quite much on the system. There have been already several decades ago quite many studies, doctoral theses showing that at least for solder interconnections, this is not true. So you cannot basically use this. It does not give any reasonable value. But the solder interconnections, of course, are quite specific because they're so dependent on, let's say, this over acceleration being low temperature melting point materials. So this could be, of course, utilized in some other, let's say, types of designs or types of products or whatever. But anyway, the point was that now they have shown that here is a process. It is patented process, and now they also say that, okay, based on this patent, we also provide you a software which basically does the same thing for you automatically. So how do you then use this AFR, average failure rate estimator, which is their, let's say, software product? And now I have to say that I don't know what is the latest version of this. So this what I now show is comes from a few years back when we did this, let's say, one of the world's largest telecommunication system provider companies asked that they would like to start using this kind of an approach. Would we, let's say, dig a little bit more into it and see if they should invest on that or not? Because they already have hull chambers, for example, in Oulu. So now most of you know what company I'm talking about. But anyway, so they were considering that should they purchase also this software so that they could, let's say, for example, model their base stations and verify the the random failures based on this software. And then of course, we didn't have the actual software because that was really expensive. So we just went through all the data which this company has kind of presented, or let's say all data which is public. So in addition to this this US patent, which is of course public, they also have let's say made few conference presentations and few, let's say, in quotes, journal papers, not very scientific ones, but we could get at least some kind of an idea what is behind this software. And I will show just a few slides on that. So basically what they say is that the software has a kind of input matrix. So these green cells here are something which basically the user inputs, and then this purple ones or pink ones, whatever is the color, is the output. So basically that is what the software is giving. So now, as you can see, there are basically 6 values which the user must input, and then there's the rest 4. These are just number of samples which is coming from the statistical mathematics, so you can get the confidence levels. But basically, out of these 6 values, then the software calculates you the average failure rate or mean time between failures. And what are these 6 values? And when we look at it a little bit more carefully, we see that there are 4 values here, which is marked with this red dashed rectangle. They are the test results, or some results related to the testing. And then these 2 values which are inside the blue rectangle, these are something else. This is related to the technology and product category. So in next slide I will show what these are. But let's first start with these ones. So what you have here is you have the original MTBF value. So basically this is again the same thing, what we calculate from the, for example, with the Mill Handbook. Then you have the final value for the product thermal test. So what was the maximum temperature after the corrective actions which you achieved? Then what was the minimum temperature after the cold temperature step test? And then what was the maximum G value in the random vibration? So instead of having the original and final values for all 5 tests, in fact, what they have only is the final 3 values. So maximum temperature, minimum temperature, and maximum vibration. And then in addition to these 2 values, which are shown, here. So first, first there's this kind of a product specification and vibration technology. And vibration technology, it is just number 1, 2, or 3, and this is based on their equipment. Maybe you remember that last time I said that this kind of a method which they use these so-called pneumatic hammers in order to make the random vibration. It's not that good when you go to very low frequencies. So you don't get, let's say, stable accelerations when you go close to a few hertz. And then because of that problem, then they have, let's say, 2 different equipment which have better capability of low frequencies and better capability of very low frequencies, meaning that they have somehow modified their vibration technology so that you can also have very low frequency, high enough accelerations there. So that is basically, to sum up, this is just pick up what machine you have purchased from them. And then the 5th number is that you need to, let's say, pick one out of these 6 categories where your product is belonging. So basically, based on the temperature specifications that your product has, So here are the use temperature specifications. If your product is specified as it should be operational between -10 to +50, then it is considered as a high performance application, and you pick number 3. And then here are the, let's say, the guard band limits. So if these are the operational specifications, then the customer specification, then the operational specification should be something like this. So operational limits which you define. So now, kind of to sum up, you have an initial value with from the, let's say, reliability calculations. Then you have 3 numbers coming from the maximum temperature your product can withstand, the minimum temperature your product can withstand, and the maximum vibration your product can withstand. And then you pick which category it belongs and which kind of equipment you have for health testing. And then basically, based on these numbers, then the, let's say, software gives you the actual final failure rate. There's one additional thing that if you input here something which is below 40,000, then the system automatically changes to 40,000. So, or if you leave it open, then also it puts it to 40,000. So now it's, let's say, another question mark that you are starting with a number which is, let's say, arbitrary number, and then you end up with something. So can that be, let's say, reliable estimation? First answer would be definitely no, because there's too many uncertainties. You start with a number which is not true, then you multiply or play with numbers which are not really based on the patent even itself, and even that was criticized. But on the other hand, what is the value of this, let's say, product, this software, is that it has quite large library, reference library. So because these kind of equipment have been sold already for several decades. So basically, this company has collected data from their customers. So which kind of test data the customers have obtained, and then what kind of field data they have, let's say, reached. And now by collecting huge amount of data, then they can basically, the software can compare, let's say, similar type of products which have been tested previously, and the test has given these kind of values, test values, and then they know that, okay, in normal use operations, they have withstand it, let's say, without exceeding these failure rates or whatever. And then based on that, the software is giving the number. So on one side, I would say that there's no scientific justification that, sorry, this value here has, or these 2 values here have any meaning. But on the other hand, as they are somehow based on long experience and large amount of data, then they can be reliable. So for me, it's really difficult to say that, okay, is this worth of the money, which I don't know what the actually the software costs, but I would assume that if a company is willing to pay us several tens of thousands of euros just to check it, if this is valuable or not, then most probably the cost of the software is also, let's say, at least in that order of magnitude. Okay, so hopefully you got the some kind of an idea that what is behind this kind of an, let's say, business, and maybe my point was to let's say, input some of the critical thinking what you need to do to really do, so that you cannot blindly rely on the sales engineer which is selling you something with who claims that, okay, with this new tool you get excellent new lifetime estimations, but you need to understand how you utilize those. And of course, always these kind of things are very good for comparing things. So now if you have several different products, different product categories, several different test results, and then you already have obtained field data, then it could be really useful to see that, okay, this new product generation or new design, will it be more reliable, less reliable? If more reliable, how much more we could promise to our customers? Okay, with these new things, we have been able to push down the failure rate with 20% or 50%, and by that you could maybe make the difference between your competitors. Okay, so basically that kind of concluded the halt part of our reliability testing, and now we can jump into the next phase. So now we have, let's say, completed stage 1 and stage 2, and the idea is now that we are here, we have been able to find all the weakest links in our design, all the design mistakes, and basically now we have fixed the design. So we have achieved a certain reliability level. Hopefully we are here. So we already are in the target reliability, but now we need to verify it. So we are sure that now we can achieve reliability which is high enough, both from the robustness point of view and both from the long-term reliability point of view. But as these tests were mainly related to the random failures, then we still don't know what will be the actual lifetime. And now with these tests, these accelerated life tests and DMT, design maturity testing, so we test if our design is mature enough, we would like to verify the long-term reliability, the lifetime of the product. Okay. The data for the software to estimate are collected individual product service basis, or they can be collected at a general level. Can the same reference data be used to test other product or service? Okay, maybe I'm not sure if I understood it correctly, but basically this data is or the software is meant for a specific product and or sample or samples, and how you use that in order to estimate what would be the failure rate for that specific product when you have the test results which were coming from the health testing. So basically you should have a product which you have tested with health testing, and then this software kind of gives you the number how what should be the failure rate in the field. But of course you could, as if I understand your question correctly, you could basically utilize it, this one a little bit more widely. So you have your different products and or different services, whatever you are analyzing. Of course, service we cannot kind of test, but if you think that the service is the product plus something else, then you can collect the data and then use your own competencies to analyze in let's say in more generic level, so that this gives you a part of the big picture. That's how would I kind of answer it in this. Okay, good. So yeah, so now let's jump to this accelerated life testing and see how does it differ from these tests, and maybe we go a little bit more deep into the testing itself. So what kind of test one should decide, what kind of stresses one could use, and so on. So let's start with the let's say quite simple definitions. first of all, when we are talking about reliability testing, accelerated reliability testing, live testing, or whatever, so the reliability testing is kind of meant that you have some kind of a controlled test, laboratory tests, where you know the stress conditions, so you know which kind of stresses you have, and then you evaluate the lifetime, the lifespan of the either device, product, system, or whatever. And accelerated is naturally is then when you increase the stress levels higher than those what the system typically faces in the normal operational conditions. So you use higher stresses, higher temperatures, lower temperatures, higher vibrations, higher mechanical circuit loads, higher voltages, higher powers, whatever, higher currents. So the stress which you use is higher than what the product would see in the normal operation. And then maybe even the main point is that by using this certain stress, higher stress, you cause something which is measurable or detectable and measurable. So you can somehow monitor. So it's not only that the product explodes or smoke comes out, but you can somehow monitor the behavior, the functionality of the device under test during the testing. So for example, you can monitor how the resistance of the an interconnection is changing as a function of testing time or something like that. So preferably it is some kind of an operational characteristic which you monitor. So therefore also, as I emphasize in health testing, that you should be able to monitor the functionality of the product during the test. In health testing, it is even more critical. So because then you really know what you are testing, what you are accelerating. And then, as already mentioned several times, we need to have utilize all three different tools. We have the actual testing itself. Then we have statistical mathematics, which can, let's say, help us in understanding a huge amount of data. And then we have the failure physics, which then we can, let's say, understand a certain data point. So when we have the statistical data, then basically we can go on and pick some of those points there and analyze it and really verify that, okay, our assumptions are correct. So this data point belongs to this distribution and the other data point does not. And this is something which also is coming in the examples later on. Okay, so now, so far we have been thinking that, okay, we have testing, and testing gives us either the failure rate or it gives us the lifetime. But in fact, reliability testing and accelerated reliability testing can be utilized in several different ways. Several other purposes also, that only these. They are, of course, all interlinked, but there are some additional things. Okay, a question. Are there possible threats to human health considering as failure modes? And if so, how is this measure tested in accelerated conditions? Yes, so basically, if I understood again correctly, the question, this is one of the points. So in fact, it is where it is here, here. So discovering problems with safety and accident countermeasures. So one of the points for accelerated or in general reliability testing, stress testing, is to find possible problems with safety. That is quite obvious. You as an electrical engineer, you have all these electrical safety related regulations. So you need to have lots of verification, qualification tests, so that you can even sell your product, you get it CE stamped so that it's safe. But you can also use reliability testing to, let's say, figure out accident countermeasures. So meaning that if this happens, then how should I, let's say, improve the product so that it won't cause any, let's say, life-threatening or injury. So, for example, maybe I already mentioned this once. This in failure modes and effect analysis. Let's say, a few years back, I was instructing a master thesis, which was basically related to safety switch of this very large electrical motors. So their safety switch kind of cannot be just that you cut off the power, because the motor is still rotating and there's still lots of energy inside the motor when it's massive. It has a high rotation speed, and then if you just cut off the electricity, that's not kind of the complete picture. Then you need to do also the, let's say, the shutdown process in a controlled way. And one of our students made a failure mode and criticality analysis on that specific safety switch part of the system. So there are several different, let's say, purposes you could, for example, I have used, when we had still this contact teaching, we did this kind of a lecture exercise about brainstorming this different kind of purposes, and there I had an example that you have a greenhouse, and then you have a lighting system there. So you need certain types of lights in your greenhouse, but you also need to put water in your plants. So one, let's say, testing purpose for this kind of a lamp would be that if somebody accidentally sprays water on the lamp, what happens? Is it sealed well enough, and to be sure that this person, the gardener, does not get electrical shock, or the lighting system will kind of crash completely. So these kind of things, these are one of the purposes, or could be one of the purposes for stress testing. I hope that I kind of answered your question. Okay, good, thanks. So that is one thing. Here is a list of other purposes. So of course, this what we have already discussed quite much is the evaluating the lifespan of the devices. But there are also quite many things for halt testing, where I mentioned that, okay, the one nice thing with halt testing is that you can, let's say, at least semi-quantitatively compare things. So you can compare designs. Shall I place this component here or there? And then you can do the vibration testing and see that, okay, now it's better to have this large transformer here rather than here, because it causes larger bendings on certain positions. You can compare components. Should I select a component from this manufacturer or that manufacturer? So for example, in the last part of the course, we are comparing different. I show that which kind of failures you can have, for example, in very simple components like ceramic capacitors. Also there, you can have different structures. For example, how much they can withstand stresses, bendings, and so on. Different processes. So should I use what type of soldering process I can use? Because different soldering processes provide you different solder microstructures, depending, for example, on the cooling rate. So how rapid the cooling is, the more rapid it is. So the smaller is the grain size, meaning that the stronger are the solder joints, but they are less flexible. Different materials. So this is very, very typical. So for example, you have in your print wiring board, you can pick up different materials from different suppliers. They all have, even they all would be, let's say, counted in the same category. They would be FR4s, flame redundant glass 4. Still, the epoxy can be different, the glass fibers can be different, the copper can be different, it can have different layout in every layer and so on, so you can compare. So okay, should I pick this structure and these materials, or that structure and those materials from this or that provider? Investigating or developing new test methods. Of course, for a company, this may not be that let's say important but for example, for us, this was maybe the most important thing during the first decade of this millennia, because we were very much developing new test methods for lead-free soldiers, for portable products. So for example, which kind of tests you should develop in order to understand how these type of devices, handheld mobile devices, how they withstand dropping. So this kind of mechanical shock loading test. So that was really important for us. Then of course we have all these, let's say, official requirements, qualification tests, and as I already mentioned, in the medical electronics and automotive side, so you cannot sell your product if you are not able to show that, okay, these products are qualified to certain purpose, to certain environments, to certain applications, and so on. Finding out possible failure mechanisms. So basically, this is a let's say tool for reliability engineer to identify and improve the reliability, and this is important. So NFF, no failure found or not failure found, or NTF, no trouble found. So these products, when I discuss with the reliability engineers from companies, they always have this problem that the customer says that, okay, this is not working, we have a problem here. Then there's your service engineer goes there and basically either fixes it or cannot fix it or replace, let's say, a motherboard or whatever. And then the problem is solved. You get the motherboard or card or whatever back, and then you put it in your test track, and it says that, okay, it's working perfectly. There's no, let's say, electrically it is working as it should be. And now the question is, okay, your customer said that it is not working. It was replaced with a new one, and now your customer is happy, or maybe at least satisfied, and now you have a product which your customer says it's not working, but when you put it into your electrical test bench, it says that no failures. It's working perfectly. And now quite often this is a question of a failure, which is kind of what would be the correct word of that. It is a failure which is seen only under certain circumstances, certain conditions. So when let's say we are talking about now board, motherboard or whatever, printed circuit card, when it's in room temperature, standing still, you measure it, everything is fine. But when you, for example, put it close to a vibrating motor, it starts vibrating, then it's not working anymore. Or you heat it up, you put powers on, you have power losses, you have the use ambient. So basically, instead of room temperature, the components are on average 60 degrees or whatever. Then it's not working anymore. So these kind of problems, which really often are related to some kind of connection, which is not good if the product is stressed. So basically, for example, you can have a connector contact, which is just based on the mechanical contact. So now the resistance is quite low, but then when you start vibrating it or you start heating it up, it bends and it opens. So locally the resistance is increased, and that's the reason that your customer said, okay, it's not operational. So by using these kind of tests, so for example, you not only you do the electrical testing in your test bench, but you do the same electrical testing by putting the whole system in the furnace and adjusting the temperature up to 60 degrees or 80 degrees or whatever. So you heat it up, and then you might find the actual problem. Because of course, what you would like to get is to understand why your customer said that this is not working, so you can do the corrective actions. You can improve, for example, in the next project generation, the design or whatever. Okay, so maybe too much time was spent on this one, but this is still anyway important part of the reliability engineer's work to really understand the field failures, and that is really critical thing. Okay, collecting data, determining the distribution. So for example, in order to compare if your let's say failure mechanism in your test is the same as in the field, then of course you need to have the data from both. So you want to collect the data so that you can compare the slopes in your Weibull analysis, so that you basically can then say that, okay, this is correct failure mechanism. You can use it just for commercial aspects, so to make the difference between your competitors. So say that, okay, we can prove that our product, the average lifetime is at least 20 years, and we have proven it this way. Okay, so this means that you have huge amount of different purposes. So of course you also have huge amount of different tests. Okay, let's jump to the next page. So I think most of these things I have already mentioned, but once more just to highlight that the main difference between ALT and HALT, so halt testing, is that ALT tests are typically using stresses which are more relevant from the use environment. The stresses are lower, so it is not over accelerating, and the target is to understand wear out mechanisms, not these random failures. So these three things are the critical key differences between halt and alt testing. We try to understand the failure modes and mechanisms in both, but here we target more on wear out mechanisms. And the other thing is that in halt testing, we typically use some kind of a prototypes, breadboards, or even complete products. So very complex. So basically, as I said, we could basically test with halt testing the whole phone, or the whole watch, or the whole, let's say, hard drive, whatever. But with ALT testing, you typically concentrate on individual parts assembly. So basically, you tear down the product and you test separately, let's say, the display with the stresses which are relevant to the display. So if we think about these things, most probably this display does not break because of, let's say, power variations inside the phone, because of power cycling. It is, let's say, 99.9% the failure is because it's dropped. It's a mechanical shock loading. So that's the way to test certain parts. So we don't test the whole product, we test parts, and we can even test one specific component, and it could be kind of a let's say, test design. It does not have to be that the component is assembled in the actual motherboard, but we could have a test board, for example, containing 15 of those components, and we can test 15 of them simultaneously if we are sure that the stress condition is correct. So it could kind of be said like that the test is adequately designed, it's carefully conducted and properly interpreted, so that you think more, how do I do the testing, what do I measure, how do I control the test, and how do I then kind of get the actual final results, so that I would really get prediction for failure probability as a function of the use time. So what about these stresses then? So in health testing, we were mainly talking about temperature, thermal shock, and vibration. But of course, as previously was shown, there are different types of stresses, and basically we can consider all these 4 categories. Of course, there are other categories also, like radiations and pressure and these things, which are maybe related more to the, let's say, some specific areas, industrial areas like avionics or space or whatever. But if we now consider more generically, then I think we could kind of divide our stresses, which are most commonly used in reliability testing. They are the chemical, mechanical, thermal, or electrical. And whatever stress we use, our purpose is, let's say, almost always try to understand or try to get the acceleration factor. So again, the acceleration factor is the ratio between the lifetime in the use conditions and test conditions. So basically, you can estimate the number of cycles. This N here just means number of cycles to failure in the field conditions. You have your number of cycles in the test conditions, and then you know this ratio. So if you have acceleration factor of 1000, it means that if your cycles to failure in your test is 1000, then that means that the cycles to failure is 1000 multiplied by 1000, which, if I'm correct, is 1 million cycles to failure. Or it could be time to failure. So if your testing time is 1000 hours and your acceleration factor is 100, then your time to failure in your use condition is 100,000 hours. So this is what we want. We want to have this number, and we want to understand that it is really a correct number. And as already mentioned, I think it was in the first or second lecture, most of our models which give us this acceleration factor contain this Arrhenius part. So this thermal activation. So the effect of temperature. So here we have again the field temperature, and this is our test temperature, and this is the Arrhenius equation. So with that we can get the acceleration factor. So if the typical field use temperature is 60 degrees centigrade and we do our testing in 100 degrees centigrade, then we have, let's say, 40 degrees above the normal field conditions. So how much this accelerates the failure mechanism. So as a rule of thumb, that could be 10 to 20 degrees, and then the lifetime is cut to half. So then that could be, the acceleration could be something like 4 or up to 16 maybe, typically, depending on the system. It's like this, if we go from 60 to 100. So, sorry, again, this same picture. So this is what we want. So field conditions, 90 degrees centigrade, test conditions at 150, time to failure in field, something like 5,000 hours, time to failure in test, something like 140 hours, then the acceleration factor is roughly 35. So by increasing the temperature with 60 degrees in the test, we have an acceleration of 35 times faster we get the results. And now the point is that, is this acceleration relevant? So are we sure that the failures which we observe in the test are the same as what we observe in the field? So that is the, let's say, the biggest and maybe the only question related to the reliability testing, accelerated reliability testing. So how much we can accelerate so that we are still relevant. And now again, from the statistical mathematics point of view, this looks good. So we have the same slope. We can basically estimate that, okay, these failure mechanisms could be the same. But of course, that is not the complete truth. We can still end up with the same slope, even the failure mechanisms would be different. But at least there is a strong indication that now our test has planned correctly. It could be that if we further increase this one up to, let's say, 175 degrees centigrade, then this slope, for example, goes like that, or goes like that, and then it means that, okay, now something happened, some material, let's say, threshold was exceeded, and the failures are completely different, and then your test results are, let's say, nonsense. Okay, so what needs to be emphasized is that there's not one universal standard for accelerated reliability testing. I think this is quite obvious already now, but there are dozens or hundreds of different types of tests where the purpose is slightly different because you have, for example, different applications. So we have these generic standards like IEC, International Electrotechnical Commission, which is a global standardization organization which produces standards for generic purpose. But then we have these standards which are, for example, field dependent. I mean, the application depends, like AEC, so these automotive standards. And they might have similar, or they have same tests like thermal cycling, but they might have different requirements. They might have different, let's say, parameters. For example, what would be what are the minimum temperatures typically used? What are the maximum temperatures? What are the durations of the test? So how many cycles you typically do, and so on and so on. Because of course we have huge amount of different environments, operational environments, and the product itself affects on the stresses, as we have been already mentioning several times. So we have the internal stresses and we have the external stresses, and then the actual stress, what the product sees, is a combination of those. We have different requirements. We have different requirements concerning the lifetime, and we have different requirements concerning the acceptable failure rates, so the random failures. And when technology evolves, then of course the test must evolve too. So thinking about, for example, displays. So how, if you compare the robustness of the, let's say, mobile phone from 15 years back, so the technology, display technology was completely different, and the display size was typically something like this. And now we have very large displays. The display technology is completely different. The customer wants definitely have rounded shapes in the display, and show that the display is basically covering the whole device, not that you have some frames here which could protect, for example, if the shock impact is coming from the corner or whatever. So it means that you need to decide new types of tests also. So now I don't want to go into details. This is just let's say, flow chart from the Dana Crow's Design for Reliability book, just to show that, okay, you have certain number of samples, and then these samples can go take a route into different tests. So for example, here you have, let's say, 100 samples which you start with, then you go, all those go to electrical and visual inspection, some of those go to drop testing, some of them have CPK capability analysis, so meaning that they are measured in different hot temperatures, cold temperatures, and so on. Then some of the samples go to live race, and the other samples go to high temperature operational life, so 150 degrees for certain times, for example. Some of the samples go to temperature cycling, some of the samples go to hot and humid conditions, and after the test you redo these same analysis and see how these tests have affected on the performance of the samples and so on. So this is just to highlight that, okay, you have several different types of tests, and now during the next few lectures, we are concentrating on some of these different types of tests. But first, we have let's say, a little bit of brainstorming that what kind of testing conditions one should use in order to really understand what is happening there. And now, basically, we can divide our stress conditions so that we have so-called single parameter tests, and then we have, on the other hand, concurrent or sequential multi-parameter tests. And now the point here is just to think maybe more qualitatively that what is the difference between these. So both of these have advantages and both of them have disadvantages. So if we start from these single parameter tests, the main advantage is that the stress condition is, let's say, simple enough that we can have a better understanding what really is happening in the product during this. So maybe the most simple single parameter test could be high or low temperature exposures. So you just put your product or test board in 60 degrees or -40 and see what is happening. Then I have put here in italic some of the tests which typically are considered as single parameter tests. Even inside the test, there are, let's say, several parameters, but they are interdependent. Like, for example, humidity testing. We are talking about relative humidity, but relative humidity is dependent on the temperature. This is an issue which we not maybe next week or next lecture or next week we will go into detail. So what is the correlation here? So it means that basically we cannot change without changing the other. So therefore we can consider these as a, let's say, single parameter tests. The same is with, let's say, power cycling. Power cycling, basically you can define what is the power which you use, and then also what is the power on time and power off time. So in fact, in here you already have 3 parameters which you can change. But still, these are all considered as single parameter tests. And basically, as I said, the advantage is we can understand more easily what is happening, and also we have our models are, let's say, more established, and maybe even, like I say, that we have simple models to model what is happening in these tests. So here are just again an example which is giving that here we have the, let's say, the test, high temperature operational life, temperature humidity bias, so hot and humid, and temperature cycling. So this is what kind of a test we have, and then for all of these tests we have this kind of a relatively simple acceleration model. So as I said already a few times, for the temperature we have the Arrhenius model. For the hot and humid conditions, we have so-called Halber-Beck model, for example, which contains the temperature part is the same, Arrhenius part, and then there is something which is related to the acceleration of the relative humidity. And then we have the acceleration factor for these 2, let's say, parameters. For the temperature cycling, we have this, let's say, classical Coffin-Manson equation for fatigue failure. So this is this has developed from the, let's say, from the mechanical engineering there in rotating axles and cyclic bending. This kind of a method model have been used for, let's say, maybe even close to 100 years already, at least several decades. So these models are, let's say, quite simple. But of course, on the other hand, we know that in the actual use conditions, we never have only one single stress which is, let's say, affecting your product reliability. but we have several of those. They can be concurrent, meaning that simultaneously there are several stresses. And this is just a list of different types of stresses and their, let's say, typically used multi-parameters test. So it could be only that you have either high or low temperature, and then you have some electrical stress or some mechanical stress. So for example, you are doing your vibration testing at different temperatures, or you are doing your mechanical shock loading, drop testing, whatever, at different temperatures. Or you have your electrical biasing at different temperatures, or you have your electrical biasing under hot and humid conditions. And then basically the case example, which will be, let me see if Jonas has already sent it to me. Just a second, I will just check if, yeah, so most probably that case example will be available in my courses within the next few hours. So you will see how this, let's say, compound loading condition, simultaneous thermal cycling and power cycling, how that is done in ABB for IGBT modules. So these modules which you use to control the rotation speed of an electric motor, and which kind of lifetime models is used in order to predict how this kind of compound loading condition is, how you can, let's say, estimate the cumulative effect of two stresses. So I will inform you when that short video is there available. So please look it through, because I think it's really good example on how these kind of concurrent tests can be utilized, and also how you do the let's say the mathematics. It does not have the let's say very deep details on how the calculations are done, and as I said, it's not the core thing in this course, but for the important thing is that you understand what are the basic let's say principles for the estimation of combining several stresses. Okay, so here are other types of combined loading conditions. So for example, corrosion together with some power cycling or whatever. So in the two final lectures of this second part, so in fact within 2 weeks we go on to these tests in more detail. So now in concurrent testing, the point was that simultaneously you have several stresses, but you can also have sequential testing, meaning that first you use certain stress, let's say, to age the sample, and then you need another stress to kill the sample. So I would say that this is somewhere, the complexity is somewhere in between the single parameter test and the concurrent multi-parameter test. Because when you use this kind of a thing, that first, for example, you use thermal aging, and then you do some mechanical testing. Then you can monitor how the structure is evolving during thermal aging, and then you can see what is the effect of this microstructural evolution in the actual mechanical loading. So this is what, for example, we are doing in our research project, let's say on daily basis, that we manufacture certain bonds, we put them in the furnace, and then we measure the mechanical strength, like just tensile strength in virgin condition as bonded, and then after certain aging treatments. And then we can see that, okay, we can estimate that, okay, how this aging affects on the mechanical reliability, and with that we can a little bit better understand that, okay, what is the weakest link, what we can do in order to improve, and so on and so on. Okay, so then we still have a few more minutes. This time I don't want to go overtime because I've done it always. So or almost always. So just a few more slides on these damage models. So as I said, this ABB case with Jonas is now currently recording for you. That will be, let's say, one example of how you can estimate the combined effects of several stresses. It's kind of based on this kind of idea what is shown here. So you have different stresses, and then you consider what kind of damage each stress have, and then you, let's say, sum up those damages. So basically, this is kind of the classical approach, so which is called incremental damage superpositioning, meaning that you have mechanical loading, you have thermal loading, you have electrical loading, and then, for example, the electrical loading causes two different types of let's say, damages. It causes the electromigration damage. So when the current density is high, the materials start to diffuse along with the current flow or electron flux and causes changes. And then you have, in addition, you have the Joule heating. Because of high local current densities, you increase the local temperature, then that causes plastic deformation. And also basically similar type of damage, which also the high operational temperature causes. So you have two different plastic deformations. And then you sum up these. So you have your electromigration or electrical damage, you have your thermal damage, and then you have your mechanical damage. And then the total damage is some kind of a sum of all these damages with different sources. And then your lifetime estimation is based on the idea that your lifetime or cycles to failure is somehow proportional or inversely proportional to the damage. So the larger is the cumulative damage, then the shorter is the lifetime. And of course, this what this kind of excludes is the interaction between these stresses. So it's kind of just 1 plus 1 plus 1 is 3, and 3 then damage 3 tells us something about the lifetime estimation. So what this is kind of lacking, it's lacking, for example, that what these stresses are doing for the actual microstructure, because this kind of assumes that the structure is, let's say, constant, and it withstands certain amount of damage, and then it fails. So basically that you have a starting value, then you have a, let's say, the damage value, and then different stresses are increasing your damage, and then when you reach the actual maximum damage, then it fails. So you are summing up the damages, but the interaction between the stresses are excluded here in these kind of models. So therefore, in fact, one of my previous colleagues, Juha Karppinen, from whom I also stole these few slides from the automotive, now in fact he is working in let's say, electric production side. Cannot remember now, recall the name of the company. He was in Helsinki Energy for several years, but now he's in the CEO or some director in a smaller company. But anyway, he did his PhD thesis on this kind of an issue, that how you should approach these cumulative stresses. So basically, you should understand how all these stresses affect on the actual materials themselves. So how material microstructure is, let's say, evolving, how defect structure is evolving, and how the strength of the material is possibly decreasing because of this material evolution. So if you are interested, I have here the link for his thesis. Is even it's already more than 10 years old, but I would say that it's still very, very valid because this is an area where we are still struggling in the reliability testing. So basically, the idea is that all these stresses which were shown in the previous slide, now what you consider is that how these stresses are changing the material properties, how the microstructure is evolving, and how this microstructure can withstand different stresses. And then based on that, you can, let's say, formulate your complete model for the, let's say, lifetime of the system. So of course, this is much more complex, but it is, let's say, a direction where one needs to go in order to really understand that reliability better. Okay, I think that now it's only a few more minutes left, so I think it's good to stop here. So we'll continue from the reliability testing also next on Thursday, and the main point there would be then screening. So jumping into the next phase in our stage gate process. I still show you a few more slides on this reliability testing in general. So kind of conclude this part, and please then check the video, case video from ABV when it's available in my courses. I will inform you when it's uploaded there. So again, I will now stop the record.